rank the conjugate bases of each group of acids in order of increasing basicity. So since these are given as acids, the first thing we need to do is draw the conjugate bases. The conjugate base of ammonia, meaning you have to deprotonate it, its conjugate base is going to be NH2 minus, excuse me, with a negative charge. The conjugate base of water, H2O, is OH minus. And the conjugate base of methane is CH3 minus. Let's go ahead and rank the basicity. So which of these anions is the most stable? Well, the only things that are attached to these atoms with a negative charge are hydrogens, right? So nitrogen with 2 hydrogens, oxygen with a hydrogen, and methyl with 3 hydrogens. So it comes down to electronegativity. Which is most stable with a negative charge? Well, oxygen is, because it has the greatest electronegativity. So what that tells us is this compound is the most stable. Therefore, water was the strongest acid. So ranking the bases in order, this is going to be the weakest base because it was the strongest acid. There's 2 ways to look at this. Weakest base because the base, conjugate base, is the most stable, the least reactive. So the more stable an intermediate is, an anion, a cation, any intermediate, the more stable it is, the less reactive it is. So this one is least reactive as a base in these group of 3. Okay. The next most reactive is going to be NH2 minus because it is the next most reactive. Again, just ranking electronegativities. Oxygen is the most electronegative, making this intermediate the most stable. Nitrogen is the next most electronegative, making this the next most stable, and a little less reactive, actually much less reactive than CH3 minus. This one just comes down to electronegativity. For the next part, again, we need to draw the conjugate bases. It doesn't matter which hydrogen you remove, all 4 of them are the same by symmetry. Let's just look at the problem again. Yep, that's supposed to be a triple bond. Remove one of the hydrogens of acetylene. You get to this as your conjugate base. And then methane. Same as here, we're forming a carbanion. Okay, so these are our 3 conjugate bases for part B. Well, the only difference between these is A, the number of hydrogens attached to that carbon, but more importantly, the hybridization of the carbons. We learned last chapter that the more S character you have to a hybridized orbital, the smaller that orbital is. Therefore, if you put a lone pair of electrons in that orbital, it'll be held closer to that atom and it will be more stable. So what do I mean by that? Let's look at CH3 first. What is the hybridization of this? Well, it's sp3 hybridized. This lone pair of electrons is in an sp3 orbital. If we move over to ethylene, so the anion of ethylene, this is now sp2 hybridized, and the lone pair is in an sp2 hybridized orbital. Here, this carbon is sp hybridized, and its lone pair of electrons is in an sp hybridized orbital. So, what consequence does this have? Well, the sp3 orbital is 25% S. The sp2 hybridized orbital is 33% s. And the sp orbital is 50% s. Again, the more s character an orbital has, the smaller it is. Therefore, this orbital is smaller than the other two. Consequently, the lone pair that is put into it is held closer to this carbon than for either the other two compounds. Since that's the case, it is more stable in this orbital, therefore less reactive, less likely to act as a base because the carbon is holding on to it tighter than these other two carbons. Therefore, the acetylene derivative is the least basic. Then the ethylene, because it's 33% S, this orbital is still smaller than the sp3 hybridized orbital, so it's pulling its electron density closer to carbon than here, making this one more stable than the methane derivative, and therefore less reactive as a base. So this one comes next. And finally, the sp3 hybridized derivative is going to be the most basic of this set of three.